Okay, so recording is in progress. And I suppose students in the room, is the size of the displayed screen okay? Or would you want it to be a little bit bigger than this? Is this sufficient? I'm just doing this so that we can sort of monitor the chat box simultaneously. Yesterday, there were lots of complaints about people being ignored online. So let's catch that. Um, all right, so we are talking about performance, role of performance, right? How do you compare computers? Uh, and in the last class, we talked about several metrics, CPI, MIPS, CPU execution time, a lot of those calculations, essentially. And then we went on to what kind of averaging scheme would be best for times, for ratios, when there's a normalization involved, and so on, right? So we saw that weighted arithmetic mean worked well for computing the average CPI, computing the average bytes per instruction, average data bytes per instruction. But when we came to normalization or ratios, we observed that the weighted arithmetic mean was not giving us consistent results, because the moment you changed your normalizing computer, we got a incorrect or conflicting result. So whenever you have ratios and you're trying to normalize performance to a reference machine, then you can use geometric mean as the scheme to do averaging. That's what we had talked about. Now, today we'll start talking about benchmarks. And there is one particular source, I should say, I should mention spec.org for this. This is a publicly available website, organization that computer vendors subscribe to get a specific workload, which is a typical sort of set of programs that computers vendors would run on their computers and then submit the results to be published on this publicly available website, right? spec.org. And what they're really doing is benchmarking their computer with respect to all the others that have also published their results. And if you go to spec.org and look at CPU benchmarks, by the way, there are a lot of variations. CPU benchmarks, power benchmarks, IO benchmarks, web benchmarks, benchmarks for cloud computing. There are many categories for this. We are more interested in CPU benchmarks, and we'll also take a look at how the calculations are done for power benchmarks. Now, why are you doing this? You're doing this so that you can compare computers, right? And it is a little bit easy to get lost on that website. So what we are going to do today is we'll talk about why we need this benchmark and what could be the benchmarks at different levels in your application to the lowermost layer of hardware. What could be the ways of benchmarking things, some pros and cons, and then let's talk about some numbers. How do you calculate those spec numbers? Now, the idea is not to go into detail, because if you go into detail, there are so many nitty-gritty details that we would have to discuss. I myself am not aware of several of those things. And even if you go to the website, you may not find some of those nitty-gritty details publicly available. But we'll try to get a sense of what a benchmarking problem could look like. So benchmarks are a multi-level problem. Why are they a multi-level problem? Well, at the top, you have an application, then you have a programming language, then you have a compiler, then you have an instruction set architecture, then you have the hardware components, data path, all the way down to transistors, right? So how are you going to say benchmarks for all? That doesn't exist, right? You can have a benchmark for applications, you can have benchmarks for OS, you can have benchmarks for your CPU, which is your micro benchmarks. But it's a multi-level problem. You cannot just say application is performing really well, so my computer performs well, right? You cannot say that. Application performs well means application performs well. It could be spoiled by the ISA. It could be spoiled by the hardware. So it's a multi-level problem, and at each level, you're trying to optimize or you're looking for a specific performance metric. For example, if you're all the way at the top, a user is all the way at the top for an application, you are looking at very broad metrics. Applications per month, useful operations per second, when it comes to like a programming language. And as you go down closer to the hardware, what is happening? You are getting to more and more specific numbers, right? When you go to the instruction set architecture, you're going to be maybe looking at MIPS, which is million instructions per second, or maybe million flops, MFLOPS, million floating point instructions per second. So those could be benchmarks for the ISA. Below that, you have data path, all the way down to transistors, where you're looking at the clock rate, right? So the lower you go in terms of level, when I say lower, I'm talking about all the application all the way down to the lowest level in hardware. You're looking at more and more specific numbers. So the issue is that we should not be using benchmarks as one and all. We should be using benchmarks for each specific application benchmarks, kernel benchmarks, and so on. But those things also have their pros and cons. So on the left over here, we are listing pros of full application benchmarks, kernel benchmarks, and micro operations benchmarks or micro benchmarks. On the right, you are talking about the cons. So for full application benchmarks, which is sort of what the user interacts with, the pros are you can port that application to different operating systems that have a specific underlying hardware. So the benchmarks themselves, you could port it, right? Because I have benchmarked this application. Now it doesn't change. I have benchmarked that application. And they're pretty widely used. But the con is they are going to be very less representative of what my computer can do for me. The computing benchmarks, the overall benchmarks. So that would only be applicable for the application. Then when you go down to the kernel benchmarks, this is sort of a very tricky benchmark because OS benchmarks actually can be very easily manipulated, right? So in my opinion, these should not be taken very seriously just because, see, it's an operating system, right? So the person who is designing that operating system is also taking care of the CPU scheduler, who goes when, right? And the operating system is sort of like a medium for all the applications to run, right? That's where all your applications are running. So things in the OS could be manipulated in such a way that you get the appropriate numbers, which is why they're very easy to fool. Those are your sort of OS benchmarks. Underneath that, you have your micro benchmarks, which is down to the bottommost layer in terms of hardware. They identify peak capability and potential bottlenecks because they are looking at everything that is coming from the application side from all the way to the top. However, because you are looking at a very, very low level, peak performance and the actual performance may be very different, right? So peak performance could look very impressive, but when you start looking at the kernel benchmarks and full application benchmarks, the story might be very different. All right. So let's talk about spec. And like I said, there are many variations. The one that we are sort of just sniffing is the CPU and the power benchmark. We are just touching the surface here. There's so much detail. And you are going to be overwhelmed by the amount of data that is available on spec.org in terms of processors. You wouldn't believe that there are actually so many processors. There are so many variations on each specific processor. So last night I did this, right? Like I went to spec.org and I opened up the CPU. I just did the integer benchmarks, CPU integer benchmarks, which were published in 2006. And I kept scrolling on the processors. I spent quite a bit of time just scrolling. It just kept going. So that just goes on to show you that all these computer vendors are subscribing to that and they want their numbers to be impressive to the consumer, right? Let's go through this list here. What is an actual workload? Well, an actual workload is a set of programs that would constitute a typical user's experience, right? These are some of the programs that a user would probably run. And you're using that to compare performance between computers. So you have a particular workload, and you're using that to measure performance. SPEC stands for Standard Performance Evaluation Corporation, SPEC. And as I said, spec.org is the domain for that. There are CPU benchmarks, there are IO benchmarks, there are cloud computing benchmarks, there are web benchmarks, and so on. The power benchmarks also. And it's those benchmarks are sort of revised from time to time. They started in 1989. The most recent one that was published was 2017, so about 4 years ago. They keep updating the list because more and more vendors are providing their numbers. But the one before that, before 2017, was 2006, right? So if you go to that website, you will find benchmarks from 2006 for CPU and also for 2017. So over here, what we are looking at is the 2006 numbers. So SPEC CPU benchmarks that were conducted in 2006, right? And during this, how are you selecting sort of the set of programs that constitute the workload? Well, you're trying to make sure that the applications chosen spend more time in the CPU, less time or negligible time doing the I/O. Because if you're doing a lot of I/O, then that's not fair, right? Because they're obviously going to become slower because of the I/O. So you're trying to choose applications that focus more on the CPU, that take more attention from the CPU. And then we are also going to normalize relative to a reference machine. Now, the reference machine that was chosen for 2006 or even 2017, I was not able to look up that machine. What was the reference machine for those specific benchmarks? I couldn't find that data. Now, if you guys search around and you find that information, and it is available, I'm not even sure that if it is available or not. So if it is available and you come across it, let me know. I was not able to find it. All right, let's move forward here. Summarize as your geometric mean. We talked about geometric mean. Why do we need it? Because we are trying to normalize, and we are trying to normalize ratios, right? What ratio are you normalizing? We are normalizing the execution time ratio, also called as the SPEC ratio. The execution time ratio is also called the SPEC ratio. I will give one number to the customer so that they decide whether this CPU is better than the other one or not. One ratio, the SPEC ratio. Well, the geometric mean of the SPEC ratio, right? So let's see, what are we doing here? We are multiplying all the execution times that have been normalized to a reference machine and finding out their nth root, right? So multiply and find the nth root, geometric mean. So let's take a look at this table here. This is all the numbers for Intel Core i7. Again, CPU benchmarks, CPU integer benchmarks in 2006 for Intel Core i7. Oh, what is that? The reference machine uses UltraSPARC 2 processor. Okay. Thank you. Let's see. So on the left over here, we have the description of the program, right? Standard workload. Everybody gets the same workload. Every processor that you need to publish gets the same workload. What does it have? Some very interesting applications, very sort of intense applications as well. You have some Perl-based street programming, some block sorting, very famous C compiler. Then there is a Go game, AI-based Go game, chess game, a very intense quantum computer simulation, H.264 computer encoder, video encoder. So there are lots of applications involved in this list, which for 2006 was considered as the typical workload. Now this is for integer based, and there were 12 of them, right? So let me just write this down. In terms of integer based, so C stands for CPU, INT for integer, 2006. right? For the integer base, they were about 12. 12 CPU integer benchmarks or programs. And I believe for the floating point, they were about 17. CPU floating point 2006. Y12, Y17, that's what was chosen as a typical workload then. All right, let's move on to this guy. So what all do we have at the topmost column here? Description, the name of the program, the instruction count, the clock time, the CPI. What will these three things give me? Instruction count, expressed in billions actually, multiplied by CPI, multiplied by the clock time, actually gives me the CPU execution time, right? That was the classic equation that we saw last time. You multiply those three numbers. So you multiply these three numbers, you get execution time in seconds, because the billion and the 10 to the negative 9 is going to cancel out. Then what do you have? This execution time corresponds to what? This execution time actually corresponds to this guy, right? Intel Core i7. But there's also a reference machine, Ultra Spark 2 processor, that's running the same application. What was its execution time? Well, for the reference machine, it was this, right? Very, very slow in comparison. So you've got the execution time for an application for two processes. Now, one is reference, one is the thing under test, the CPU under test. Now, how do you find the spec ratio? You simply divide, let's see, you divide execution, not execution, you do reference divided by execution time to find the spec ratio. Bigger is better, smaller is better? Higher is better, right? So if this number was higher, that would mean that the reference machine is taking much longer than your device under test. So that's good news for it, right? So the higher is better there. And then what do you have? You have all your spec ratios for each application. You multiply all those numbers and take the 12th root, right? And then you get your one number for CPU benchmarks for Intel Core 7. And then you have those numbers, the geometric mean of the spec ratios, just listed on that website. Right? And then you can take a look and comment about, oh yeah, this CPU is doing a faster job because we are computing clock CPU times. Questions here? Some applications are sort of taking a lot of clock cycles per instruction. So for example, if you see 0.44, the quantum computer simulation is taking only 0.44 cycles per instruction. And that number, on average, it is taking 0.44. Because it's not just one instruction, right? It has 659 times 10 to the 9 instructions. So on average, it is taking 0.44. If you compare, that's the lowest side of the CPI. And it can go as high as what? 2.66. So for a combinational optimization problem here, the average CPI, so the point is the average CPI, depending on what application is being run, can vary by a lot. The number of instructions are different, CPI is different, clock cycle time is consistent, just because it's the same clocking source that is being used for that processor. Okay, let's go to the next one, which is the power benchmark. Who did a really bad job with the power benchmark? Historically, Pentium 4 screwed it up big time, right? Because they said, let us clock our machines at a higher rate, overclock things. Let's use that as the thing to make it fast. What happened? Things got heated up. I don't know if you guys have experienced the heat from Pentium 4, but it was a huge problem. So what did people do? After that, they actually put a limitation on the clock rate. They actually went down. So you would think that over the years, the clock rate has always kept going up, but that's not necessarily the case, right? You cannot just keep going up because the faster you clock things, you are going to hit a power wall because you are going to need a cooling system that can handle all that heat being generated. Now, you have another problem to this. You have another dimension to this. You have multiple cores, right? Now, if you have multiple cores, you're going to have to try to cool everything down. So what they do is sort of doing a space multiplexing. You have processor here and a processor here working, then they switch, they sort of spread it over a bigger area. But the problem is that the higher you clock things, that doesn't necessarily mean good performance. It means that you are trying harder, that you can, that you are trying very hard, right? It's going to do two things. One, increase the power consumption. Two, it is going to reduce the lifespan of your machines. So how are you calculating this power consumption? You're doing that using Java operations. SSJ stands for server-side Java operations, as opposed to what? Client-side operations. You're not doing this at a client, you're doing it at a supercomputer, at a server level. And you're executing Java operations, many of them, at different workloads. So what do? You start with, say, 100% workload. How much power is being consumed? Then you go down, 90% workload. How much power is being consumed? What should happen? If I'm operating at 100% workload, running, right? Like full on, full mode, the power is going to be higher, right? And as you go down, say 10% each time, the power, do you guys agree that it should decrease, right? It should get cooler and cooler as it goes down in terms of workload. That's exactly what's going to happen. So what we do is build a table. You have number of Java operations in one column that have been reduced by 10% each time, all the way down to 0%, right? So when you're not even running, what is the amount of power being consumed by your CPU? The power is being consumed in wattage, joules per second, and your performance is your SSJ, server-side Java operations per second. So the CPU benchmark is this. You add up all the server-side Java operations per second for every workload level, 0 to 10. What does that mean? 0%, 10%, 20%, all the way up to 100% workload. And on the denominator here, you have the power that is being consumed at each of those workload levels. And you divide them up, and that's your going to be overall power benchmark. Would you want this to be high, low? High is good, low is good? High is good, right? So if you are able to do more number of operations in lesser amount of power for lesser wattage, that's best. So high is good here. And these are the numbers for the Xeon processor power benchmarks conducted in 2008. Like I said, they start in 2006 and then they keep getting updated, right, over the course of time. This was published in 2008. On the left column here, you have the target load, 100% all the way down to 10%. In the next column, you have your number of server-side Java operations being reduced by 10% each time you go down in this column. And then the lowest entry in this table is the sum of all of these guys. Then you have the average wattage. And as we said, as you are reducing the number of the operations per second, your workload is going to get better, right? Like the power is going to go smaller. It's going to be less hot. And then you have got two numbers here. Numerator, denominator, divide it, you get a number, which is your power benchmark. And as we said, higher is good. So one number to indicate CPU performance, one number to indicate power performance. Customer is the judge. Is it going to be hot or not? Tell me the power benchmark. Is it going to be fast or not? Tell me the CPU benchmark. All right, so let's jump to our next lecture here. We had a good discussion about the role of performance of a CPU. We talked about metrics, we talked about benchmarks, which was sort of what you use to communicate about performance. You use benchmarks. Now we start looking at the intersection of your software and hardware, which is the instruction set architecture. And the next maybe 5-6 lectures are going to be sort of dealing with ISA. And the ISA that we are dealing with in this class is the MIPS ISA. Not the million instructions per second, but the microprocessor without interlocked pipeline stages. So we are again going to do this in a couple of parts. This is part 1, instruction set part 1. Now, a quick recap about the life cycle of an instruction. Where does everything start? It starts in program counter. Look at the program counter. Why? I need to know. So, Zach needs to know where that piece of paper is, right? So, go look at the program counter. You're going to find the address of the next instruction. Put that address in the MAR, perform the read cycle. You're going to get some data from the memory, which is actually the instruction that you need to execute. That's going to go to MBR. From the MBR is going to come to the IR. Completes step number 1, which is instruction fetch. Then you look at the instruction. CPU or the FSM, sorry, not the CPU, the control unit, which is the FSM, is going to observe the opcode, decode it. Based on the decoding, now it knows what instruction it is. It may need some operands. Fetch the operands from the memory. Maybe it is using the load path for that. Execute. Next step over here. After that, increment PC. Right? That's sort of the life cycle of the instruction. And I suppose that at this time, if you look at any of these components, you know what their role is, right? You know what the ALU is there for. You know what the PC is there for. IR is there for. FSM is there for. Each component in this data path, well, you have a data path along the memory as well. You know what their role is. Now, if you look at the memory, you also understand what N corresponds to, what M corresponds to, right? N is the width of the memory. And at each, how many such locations are there? 2 raised to M, because for the address space, you're using M number of bits, right? Today, we'll be focusing here. We'll be focusing in the IR. What does IR include? It includes generally, at least with the discussion that we have had, 2 things. Opcode, operand specifier, right? That was the format of the instruction register, at least with the conversation that we have had, very generic one. Opcode tells you what operation, operand specifier helps you with the details of that. Where is the operand? There are lots more details in this, and it actually depends on the type of instruction as well, right? The operand, opcode, and the operand specifier could look very different in terms of different type of instructions within the same ISA. So we'll be looking at what those details are, what are the different types, and so on. So when you look at the instruction set architecture, what is the programmer's view? Well, you need to ask a few questions. When you're trying to write this particular set of instructions to execute a program, before you do that, you need to ask a few things or few details about the ISA. The first thing that you need to ask is, what are my registers? How many do I have? What is the size of each register? So all of those are going to be answered when you look at the first main ingredient of the ISA, which is register file. Bunch of registers, right? And we know how to make registers, right? use D flip-flops for temporary storage of bits. How many registers do we have for MIPS 32? Or the MIPS I say that we are going to look at, how many registers do you have? We have 32 of them. What is the size of each register? 32 bits. Very easy to remember, right? We have 32 registers and each register is 32 bit. By the way, what is 32 bits? I can say 32 bits in many different ways, right? I can say 32 bits, or I can say 4 bytes, because each byte is 8 bits. So I can say 4 bytes. I can say one word. One word is 32 bits. Or I can say 2 half words. So one word equals 2 half words equals 4 bytes equals 32 bits. Yeah, so I can refer to them in sort of many different ways. So that's the first sort of ingredient that goes into it. What is the register file part of? It is the part of the data path. It is the part of my CPU. CPU has 2 components, data path and the control unit. This belongs to the data path. Next, memory architecture. Outside the CPU, there is a memory. That's where all the instructions are. That's where all your data operands are. Everything is over there. Slow or fast? Well, it depends. If you're talking about the RAM, fast. Hard disk, slow. But that's your second ingredient. Why do we need to know about the memory organization? Because there are 2 things that are going to be limiting. One, not limiting, I should say 2 things that are going to be, we are going to need to be careful about. One, how many address locations do I have? In other words, how many bits do you need to select each memory location? And at each memory location, how many bits do you have? Sort of the same as saying, what is N and what is M? Cap N and cap M, right? So I need to know that. How many addresses and how many bits at each address? So that's sort of the next question here. And generally that would vary depending on the memory that you're trying, the way it is organized. The one that is sort of we are going to use in our conversation is at each location you have sort of 8 bits and you have a 32-bit address. So you have a 32-bit address to pick out each memory location. And at each memory location, you have 8 bits. Now here is a question. I have a register file, part of my data path. I have a memory architecture, right? They are separate things. Which one is faster? If I wanted you to search something and I gave you 2 options, register file and the memory, where will you try to search it first to make register file, right? I have 32 registers. I have a 32-bit address space. So you have got 2 raised to 32 minus 1. Those many different locations to search for, right? So not minus 1, just 2 raised to 32. Because each byte, I'm using 32 bits to address that. So it starts at 0, ends at 2 raised to 32 minus 1. In total, it is 2 raised to 32. So on one side, you have a lot to search from. On one side, you just have 32 to search from, right? So the CPU to support instructions is going to be a lot faster. In fact, it is 100 to 200 times faster than a memory access. What does that mean? Why is that helpful information? Because when you're writing instructions, try to use the register file as much as you can. If you try to use the memory, you are going to run into things that become slow, right? And there are going to be instructions where I have to look at memory because I need that data from the memory. I need to load something from memory into my register file. Can't do anything about that. I need to store a register content into the memory. So I need to execute a store instruction. Can't do anything about that. But those are the only 2 instructions where you're actually talking to the memory. Load and store. Bring things, put things back into the memory. But all the other operations are going to be carried out within the world of register file. So they are going to be very, very quick. All right, you guys are all in agreement there? So that C register file is going to be much faster than a memory access? All right, next question, next topic is, suppose I wanted to load things, I wanted to bring something from memory to register file, right? You see a difference there? Register file is 32 bits. Memory, each byte of my memory is 8 bits. So am I bringing one memory location or am I bringing 4 to fill one register? I'm actually bringing 4, right? So I need this guy, I need this guy, I need this guy, I need this guy. All of those will go into one of these registers. Can you see that? So you have 1 byte, 1 byte, 1 byte, 1 byte, 4 bytes making up one word. So when you bring things from memory, load, or when you put things back into memory from a register, do you do load byte or do you do load word? Load word. So we have an instruction, load word, that you're going to see a lot, but it is load word. It is not load byte. And we have similarly store word, no store byte. Okay, so next, let's talk another thing here. The memory, the way I have organized it, is it byte addressable or is it word addressable? How am I addressing each location? There are two options I've given you. Byte addressable, word addressable. How does the memory organization look like? But I'm giving 32-bit address for each byte, right? So it's going to be byte addressable. So your memory is byte addressable, but when you bring things from memory or back, you're doing things per word, right? So that's a distinction that you have to be clear about. Go ahead, Zach. Just an example here. Your memory could be organized in a different way. So I'm starting us off with a memory organization as shown. Later on, you will have the option of looking at, okay, what would happen if I change this or this or this? The point is, you have a 32-bit. That's the constraint here is the 32-bit size of the registers, and there are only 32 of them. That's the only thing that is sort of fixed. The memory, the way it is organized, it could be different. But I just wanted to start us off with some numbers. Let's see. We talked about that. Right. Byte addressable memory. Right. We talked about byte addressable memory. Next, the third ingredient of a ISA is the instruction set itself. How many instructions? Add. How many integer instructions? How many floating point instructions? What is the complexity of the instructions, and so on. Why do people choose MIPS? Because it is simple. The instruction set is very regular. So in order to convey things about ISA, it is a very good starting point. Yeah, people also at times look at x86, but that's a very complicated conversation. So we'll be looking at a MIPS ISA. That's the reason why people look at MIPS ISA. It is relevant, however. You guys know where MIPS is used? MIPS 32 ISA. Nintendo switches uses MIPS reduced instruction set computer ISA. Your HP printers, your Cisco routers, your Broadcom chips, all of the Sony PlayStation, all of these things are using MIPS ISA. So it is relevant. Don't think of it as an archaic ISA. Let's see. So when you talk about the instruction set architecture, we are talking about how many instructions, what is the complexity, do we have integer instruction support, do we have floating point instruction support or not? So all of those things. Those three are sort of the main ingredients for an ISA to be observed, to write programs in the ISA. Let's see. Like I said, the MIPS ISA is what you are going to be following in KNOS. MIPS stands for microprocessor without interlocked pipeline stages. And when you start talking about pipelining, you will, that's when we can have the discussion about what each of those terms mean. It is a 32-bit reduced instruction set computer ISA. So it's a modern RISC ISA. That's what we are looking at. And it is used in Nintendo Switch, Broadcom, Cisco, Sony PlayStation, like I mentioned. More information can be obtained at mips.com. The one that we are looking at is actually MIPS 32. There are others as well. There is a MIPS FPGA. There is a MIPS 64. There are other MIPS architectures as well. The one that we are looking at is the MIPS 32. So feel free to go to that website and take a look at what are some of the details, because we will never have time to look at all the things about an ISA. But if you're interested, please take a look. MIPS register, we kind of touched on this, right? 1 word or 32 bits or 4 bytes. And I think we defined it in 2 half words as well, right? So each MIPS register, where is it? In the register file. How many are there? 32 of them. What is the size of each? 32 bits. 4 bytes. 32 bits, 1 word, or 2 half words. Next, it has 32 registers. So the obvious question is, why not 64 registers? Well, if you have things that are 32 registers, it is going to support fewer number of instructions. If you have more and more registers, then that is sort of going towards a more complex instruction set. And as a byproduct, what are you going to have? Your data path is going to look very, very complex. So what that means is, if I go all the way to the front of the page here, you look at this. This is a block diagram, right? Now, when you actually sort of zoom in to this, that's our goal, to go to the MIPS 32 data path. When you zoom into this, you are going to put details about muxes, register file. ALU will leave it as ALU. You will need shifters. You will need sign extenders. You will need comparators. A lot of those things, all the details will go into it, right? And when all those details go into it, there is a chance that you might get overwhelmed by the size of the data path, even with the 32-bit MIPS. So if you went for 64 registers, it is just going to be a too complex data path for us to be able to look at, to be able to observe, to be able to understand. So that's why we look at the 32 registers. So we look at MIPS 32 instead of MIPS 64. Variables are going to reside in registers as far as possible. Why is that? Whatever instructions you want to do, add this and this and store in this. You want to use registers. Why? Because they belong to register file. What is the alternate? Memory. Slow, bad. Use registers. What if you run out of 32 registers? What do you do then? Use memory. So yeah, I can't do anything about it. Now, I have written programs that have several procedures, right? Several functions. So suppose you have one program that has functions and functions inside functions, nested functions, you are going to run out of registers that you need. So what do? You use memory for that, right? In other words, you actually use stack for that, right? You have heard in your C programming classes, you might have heard of stack pointer, yeah? Store things onto a stack. Why are you doing that? Registers are not enough, right? So registers are not enough, you have to sort of go to memory, because that's the only place where you can store it. Registers are grouped by roles. So let's take a look at some of the, well, not some of the, all of the registers. So this table lists out the 32 registers their brief description or usage, and their number. The number is written in decimal form. However, when you actually write the machine code for each instruction, you are going to need to convert that decimal to a binary, because machine language has only binary, right? So let's take a look. 32 registers. Their names are over here. Register numbers are over here, 0 all the way down to 31. And their usage is over here. Let's talk about them. Let's start with the 0 register. What is the name? $0. Why dollar? Because I'm going to use dollar as a prefix to every register. The moment you see dollar, you know that you're talking about a register. So $0. What is its number? 0. Very easy to, that makes sense, right? 0. The number itself is 0. So whenever you want to talk about the 0 register, you are using a bunch of 0 bits. What is the usage? It is a constant that holds the value 0. You can't change it. So the user, the programmer, cannot change one register. What is it? 0 register. It is going to be 0. You try to change it, it's going to throw an error. So where could this be used? 0 register. To initialize things. A equals 0. Just use this 0 register to do like an addition operation, right? So, and we'll take a look at examples where this can be very useful. But to initialize things to 0, this can be very, very helpful, right? 0 register. Next, let's see. You have a reserved register by the assembler. 80 is the name, the register number is 1. Next, you have V0 and V1. These are 2 registers that are used to hold results and expression evaluation. So think about a function. Whenever you are writing a function, you call a function and it returns something, right? When you're calling a function, what are you passing to the function? Arguments, right? So we have certain registers that hold arguments. A0 to A3, they have their specific numbers, 4, 5, 6, and 7. Those registers, their main purpose is to pass arguments to a function, a procedure. And then the procedure is going to work on things and it is going to return value. Where are they stored? In the V0 and V1 register. Again, when we look at examples, you guys will see all of these things play out. But we are looking at things a little bit briefly here. Next, you have a bunch of temporary registers, 8 of them here and 2 more here. Why are temporary registers used? Well, whenever you're writing a program, there will be a scenario, multiple scenarios in fact, where you will need to hold things temporarily, right? And temporary registers are not just used for that, but they're also used alongside the procedures. So whenever there's a main program and there is a procedure call, you would want the main function to be sort of control some registers, those are the saved registers, and then the procedure itself will take care of the temporary registers. So one set of registers are in the purview of the main function, and the other is the purview of the nested functions or just the sub-functions. So those are your temporaries and the saved registers. Let's see, saved registers are in the middle here. So we'll be using 0 register a lot. We will be using the saved and temporary registers quite a bit. And when we start having the conversation about stack pointers and stacks, we will be using the V0, V1, the argument registers. Also, we will be talking about the stack pointer at the very bottom. We'll be talking about the stack pointer and the return address. Why do I need a return address? Well, you have, at one particular instruction, you have called a procedure. You go to the procedure. You need to know where to come back, right? So you use the return address register for that. And again, we'll find more details about this as we go on. Now, I want to point you guys to a resource that is going to be very important to have handy during homework, during activities, during exams. You are going to need to refer to this as much, a lot, right? So have that piece of paper. It is, I think, two-sided. That's it. One piece of paper, double-sided. Where is it? If you have bought the textbook, it is probably the first page or the last page. It's a green-colored cardboard that is at the front or the back of the textbook. To make things convenient for you guys, I've also uploaded it on Piazza. So if you go to Piazza, I have uploaded, let's see, this one is right here. Why didn't this, in general resources, I had uploaded it. Oh, there it is. So it looks like this. I've uploaded it. Make sure you get it. You're going to need it. Lots of details, but it will help you a lot. So for example, the one that we just looked at was right here in this table. What are the registers? What are the numbers? And what are the use? But it will also talk about the instruction set. What is the opcode? What is the function code? What is the instruction actually doing? Right? All of those details are over here. So for example, let me just walk you through the first one here, which is the add instruction. What is the name or mnemonic? Add, ADD. What type of, what is the format of instruction? What is the type of what type is this instruction? It is the R type. R stands for register. It is a register type instruction. There are three types, R, I, J. Register, immediate, jump. R, I, J. This one is R, register. What does it do? What is the format? Well, it takes two registers, RS and RT, adds them and stores the result in RD. RS plus RT, those are your two source registers. Where are the source registers? Register file. So you have an option of 32. Well, what would be appropriate usage? You wouldn't want stack pointer in this conversation, right? You wouldn't want a return address in this conversation. You definitely don't want 0 register as the destination. You may be using 0 as one of the source registers. But for the destination, what is a good choice? A saved register is a good choice. A temporary register is a good choice. But the operation is what? Take two registers, add them, put the result in a destination register. RS plus RT plus gives you something that you need to put in RD. While all of this is going on, do I have anything to do with the memory? Nope. One register in register file plus one other register in the register file, who is going to add ALU and store the result back into the register file. Quick and easy, right? How many registers do I have? 32. How many bits do I need? How many bits do I need to reference each of these source registers or the destination register? No. There are 32 registers in total. So I need 5 bits. So let's say 0, 0, 0, 0, 0. 5 zeros. Did I say 6? 0, 0, 0, 0, 0. That's for register 0. Register number 1, register number 2. So because there are 32 registers, I need 5 bits to reference each of those registers. Which means to reference each of the registers, I need a register number. Where is it? Register 0, number 0. Register, let's look at the saved registers. What if there is overflow? What do you do with overflow in 2C? Because the addition operations is going to be supported by 2's complement representation when it is signed. So the one that we saw add was the signed addition. Numbers are in 2C, you add them in 2C, result is in 2C. What do we do in overflow? What do we do for overflow in 2C addition? Oh. Well, we ignore it, right? It's on to the user to understand what they're adding and subtracting. You've got an overflow, you've got an incorrect result. That's it. It's on the user. It's not on you. Let's see. What is it? Right. So you guys understand why we need the numbers to reference each of those registers. And those numbers will later need to be converted into binary, which is a simple decimal to binary conversion. And by this time, you guys are going to be experts at that. All right. Before I make things any more complicated, let me go back to this. So summarized on the green page in the Patterson and Hennessy textbook, also uploaded on Piazza. If you have a very nice printer, you can print it out and have it handy. I have several printed in my office. If you want one, let me know. I can give it to you as well. But having it handy is going to be important. Now, this is something that happened last semester, and I don't want this to repeat. We went through all the lectures on ISA, and then there was a student who said, where can I find this information? And I went on the green page. The student said, where is the green page? So I don't want that to happen like ever again in this course. This is a very important resource for the MIPS ISA, right? Assembly, if you want to do any assembly or if you want to do any assembly to machine, you need this. All right, everybody online, 16 of you also got that. So at least I've got half the class covered with this. Let's see. All the register names begin with dollar. The one thing that I want to point out again is don't use the dollar in front of the numbers, register numbers. Use it in front of their names, right? So dollar $S0 number is 16. Okay. Now let's talk about the memory organization. And like I said, I've talked about a memory organization in which each location is 8 bits and it is byte addressable. And I'm using 32 bits for the address, right? One memory organization. Some of this is going to be repetitive. Some of this is going to be new. MIPS memory is byte addressable, which means that I can address each byte, a sequence of 8 bits. Problem? When I do load or store, I need to do that per word. So even if things are byte addressable, it is a word aligned memory. Instructions are word aligned. More about that as we go through. What does word aligned mean? Byte addressable mean? What does word aligned mean? Word aligned means 32 bits, aligned with 32 bits, aligned with 32 bits, and so on, right? Byte addressable means I can address this byte of that word, this byte of that word, this byte of that word, and so on, right? Let's look at the two sort of options here. On the left, you have the same memory, but you have aligned it word by word. Word 0, word 4, word 8, word 12, and so on. So the first question is, why is it 0, 4, 8, and so on? Well, you have got 4 bytes in the first word. So 0, 1, 2, 3 went there, 4, 5, 6, 7 went there, and then the next 4, and then the next 4, and so on. So the word address, can I say that it is always going to be a multiple of 4? Can I say that? And what is the property of, in binary, what is the property? 4, 8, 12, and so on. Anyone? 4, 8, 12, so on. What is the thing that you can pick out? Exactly. any multiple of 4, the last 2 bits are always 0. In fact, whenever you want to multiply by 2, what do? Take the number in binary, shift it left, put a 0 in there. You have multiplied it by 2. You want to multiply a number by 4? Take the number, shift it 2 places, put 2 zeros in there. In the least significant position, you have multiplied it by 4. Right? 8, move 3 places, zeros. 4 places, zeros, and so on. Right? So you can multiply by a power of 2 easily by doing that. Here, what are we doing? We are multiplying by a power of 4. So shift left 2 places while you fill those 2 spots with 2 zeros. Right? Why would we ever need to do that? Well, sometimes we need to convert an offset which is provided as a word number into a byte number because things are byte addressable. So we will get 8. We will need to multiply it by 4 so that we get 32, which is going to be the byte number for the 8th word. You see that? Yeah? No? A little bit empty. All right, let's go slow again. So here on the left here, we have a memory in which you have word after word coming in, and we are still addressing things byte wise, byte addressable. So in terms of byte, 0, 1, 2, 3 went here, right? 0, 1, 2, 3 went here, and then 4, 5, 6, 7 in the next one, and the next one, and the next one. So where did this particular word go? Now, if you start looking at things that are byte after byte, word 0 was this, right? 8-bit, 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 8-bit. So your memory looks like this, but you can sort of look at its word aligned organization. How many bits do you have to pick out each location? 32 bits, right? So if you have 32 bits, you're going to have an address space of 2 raised to 32 bytes. You give me a 32-bit location. If that is the case, if that is the address space, then you will have 2 raised to 32 such bytes, right? So 0, 1, 2, 3, all the way down to, what is the last number here? 2 raised to 32 minus 1. Those are bytes. But when you look at it in terms of words, what are you going to have? 0, 4, 8, 12, all the way down to 2 raised to 32 divided by 4 minus 1. 2 raised to 32 minus 4, right? That's what your last one is going to be. But how many words will you have? You will have 2 raised to 32 divided by 4, 2 raised to 30 words. How many number of words you have, you multiply it by 4, you will get the number of bytes. One word, 4 bytes. 2 raised to 30 words, 2 raised to 32 words, bytes. Now here is a question. Let's see, okay, so there are 2 possibilities with this. Think about word 0. When you think about word 0, what do you have? You have a 32-bit word, right? 32-bit word. In other words, it's just 32 bits, we are calling that a word, right? There are 4 bytes in that. Yeah, there are 4 bytes in this. How are they arranged? Is it byte 0, byte 1, byte 2, byte 3, or is it byte 3, byte 2, byte 1, byte 0? Which one is it? Depends on big endian or little endian, the way the memory is organized. For MIPS, it is big endian, which essentially means big endian, 0, 1, 2, 3. So we are going to strike this out. That is the little endian. In other words, The first one goes here, the second one goes here, third one goes here, fourth one goes here. It's not all the way around, right? Why do we need to talk about that? Because there is going to be a least significant byte and most significant byte. And we need to be clear about where it is, right? And I have a diagram to kind of make things a little bit more clear. Questions here? Words, bytes. Why do we have 2 raised to 32 bytes? Why do we have 2 raised to 32 minus 1 as the last byte number? So here, whenever you get confused about these sort of sizes, right? Make it slow, make it simple. 2 bits. If you had 2 bits, how many locations can you address? 4, right? 2 raised to 2 will give you 4. How many locations, how many bits do you have for a address? 32. So how many locations? 2 raised to 32. 2 raised to 32 bytes, right? So if you start at 0, you should end at 2 raised to 32 minus 1. So far, so good. When you move to the words, all you're doing is grouping 4 bytes, grouping 4 bytes, grouping 4 bytes, and so on. So things are going to get divided by 4. So instead of having 2 raised to 32 bytes, you're going to have 2 raised to 30 words. And if the sequence is 0, 4, 8, and we know why that is 0, 4, 8, right? In terms of words, it is going to be 0, 4, 8 because you have combined 4 bytes here, 4 bytes here, and so on. The last one in that sequence is going to be what? 2 raised to 32 minus 4. All right, let's see. The byte ordering conventions. There are 2 of them. Big endian, that's the one that is used for MIPS, and the little endian, which is not used for MIPS. What is the difference? Well, word 0, this is big endian. Word 0 will contain the most significant byte, and the word 3 will be the least significant byte. In other words, if you write a number, say 1, 2, why did I write 2? 0, 0, 1, right? Just assume that I have written a 32-bit sequence. Which one is the most significant? All the way to the left, right? And which one is the least significant? All the way to the right. So the first 8 will go here, the most significant byte. And the last 8 will go over here. You guys see that? So that's very intuitive, right? You have this number. Let's take the first one, put it here, second one here, third one here, and fourth one here. Right? Very sort of normal. But there is also an alternate, which is the opposite way. Let's put all the way to the left this guy over here, and then all the way to the right this guy over here, which is the little endian. That's not what we are going to do, but it's good to know that other byte ordering scheme. All right. So the same thing is sort of also captured over here. So for example, if you look at word 0, you have 0, 1, 2, 3, right? What are those? Those are byte numbers, right? Byte 0, byte 1, byte 2, byte 3. 4 bytes making up a word. What is the word number? 0. And where is that 0 going? That is that, and this guy is here, right? Let's see how that is organized. And that applies for the other things as well. For example, if you had this guy, it would go here. And when you have, say, this guy, 8, 8, 8, another 8 will go here. As opposed to what? Little endian. How does that look like? The least significant is going up front. Oh my gosh, right here. And this guy, the most significant, goes over there. Word 0 goes all the way there, word 3 goes over there. And then you keep repeating that, which is a different byte ordering convention that is not followed in MIPS. All right, let's see. Now let's talk about the word alignment restrictions. instructions, whenever you write, bless you, instructions when you write, they are word aligned instructions. And in fact, when you try to load word or store word, those are per word. But things are byte addressable. In other words, think about word 0 here and word 4 here, right? Word 0 consists of byte 0, 1, 2, 3. Word 4 consists of byte 4, 5, 6, 7, right? I'm just saying word 4, but it's not to be confused with word number 4, right? It is the second word with the starting address of 4, right? So I hope that doesn't confuse. There are no 3 words in the middle. There's word 1, 2, 3, 4. The starting address in terms of a byte is 0, 4, and so on. Now, how do you get to get byte 2? What do you do? Suppose you need this, right? I said the memory is byte addressable. So I should be able to pick out byte 2. How can I do that? I get the whole word. So I bring the whole word from where to where? From the memory to the register file, and then I will play some tricks, some other instructions to extract byte 2 from that word. You guys see that? So you want a byte, sure, you can get a byte, but you will have to load the entire word from the memory to the register file and extract the byte that you want. Now, what if I just want a word? No problem, get the word, right? How many bytes is a word? 4. Can I get any 4 bytes? In other words, if I wanted to bring this from the memory to the register file, can I do it? Right, not in one instruction. I can do it, but for that, I would need to load word 0. I need to load word at address 4, then play some tricks to sort of align those bytes in that particular order. But I need to get 2 words here. This is called a unaligned access, memory access. Unaligned memory access, believe it or not, wasn't a thing until 2010. So Intel has started doing that very recently. 2010. So, you know, for me, it's recent. For you guys, it's probably just not so very recent. But Intel has started doing that in their ISAs very recently, is what I want to say. Let's see. I think we talked about that. Words are aligned on 4 byte boundaries. We talked about that. All right. So let's quickly go through this here. Our MIPS instruction set is small. We're not going to be talking about a lot of instructions. We're going to be focusing on a few instructions. I'll give you guys examples. Add, subtract, some logical operations, and we will be looking at some shift operations, shift logical left, for example. Then we'll be looking at load word, store word memory. Load word and store word, those are the only 2 instructions that have anything to do with the memory. We'll be doing conditional instructions, branch when equal, branch when not equal. We'll be doing some jump instructions, jump, J instruction. So a small subset. We'll not be looking at floating point instructions. We'll not be looking at the entire instruction set. We'll keep things simple. But it is summarized on the green page at the beginning of the Patterns and Hennessy book. Again, important resource, please keep it handy. The design philosophy with MIPS is go simple and regular in order to get a better organization for the instruction set. So things are going to be pretty intuitive and easy to understand. There is only one way to do a task. Well, that particular statement needs a little bit of clarification. When I say only one way to do a task, that doesn't mean that there is only one right answer when you're asked to write up specific instructions. One way to do a task means if you wanted to add 2 numbers that were signed, then you would be looking at the add instruction. That's sort of what it means. But you will obviously, when you start writing the programs, you will obviously see that there are not so good ways of writing the same instruction, but they are roundabout way of doing things, which could be reduced, which you can reduce the number of instructions. So what that one way of doing a task means that there is a specific instruction meant for a specific operation. Smaller hardware is faster, so 32 registers, the data path is simple, makes it faster. And we have better compilers for MIPS instruction set. So all of this is sort of leveraging the make common case fast idea, the design principle. The first instructions we'll be looking at is the arithmetic instructions. Probably the easiest type of instructions, the R type instructions. Add is one such example. All arithmetic operations have 3 operands. What? You said instruction register has 1 opcode and 1 operand specifier. Now you're saying 3 operands. Yes. So when I say operand specifier, I'm talking about all the things that will specify operands. For R type instruction, it actually has 3 operands. There is a shift amount and there is also a function code involved. So a lot more things, a lot more fields involved. But all arithmetic instructions, examples, add, multiply, subtract, all of those are going to have 3 operands. What are those 3 operands? They're all registers. You will need 2 source registers and you will need 1 destination register. What are your choices? 32 registers, right? One of those 32 will be your source registers. Can I use the same one twice? So can I do something like register 1 plus register number 1, the result goes in register number 1. Can I do that? Yes, I can do that. So get the number from register 1, get the number from register 1, double it, put the result back into the register 1, the same register. Yes, I can do that. Let's see. What is the example here? The C code is add B plus C, store the result in A. B, C, A, these are all variables, right? That you are using in your C code. High level code, you use a compiler, you do a MIPS, the assembly, right? Let's do the assembly for this particular C code. Let us assume that we are using for the variable B, what are we using? $S1, one of the saved registers. For C, we are using one of the saved registers, $S2. For the destination, we are using another saved register, which is $S1. Can I write $S1? Will the machine understand $S1? No, it doesn't, right? It understands zeros and ones. So I'm going to need a way to convert $S1 into a 5-bit sequence, 32 registers, so I need 5 bits to identify them. Where do I need to look? MIPS reference sheet. If you look, hopefully, this will be the numbers. For S1, S0, number 16. For S1, number 17. For S2, number 18. You guys can correct me if I'm mistaken with the numbers there. So what is 16 as a 5-bit sequence? For 16, I need 16. No 8, no 4, no 2, no 1. Yeah? Then for 17, I have what? 1, 0, 0, 0, 1, 1, 0, 0, 1, 0. Can you see that? One thing to note over here is the destination is the first operand that you are mentioning, right? Destination first. Does it matter if I did add S0, S2, S1? If I change the last two, doesn't matter. Commutative, addition. If it were subtraction, then yeah, I need to worry about it. Addition, I don't need to worry about it. Multiplication, I don't need to worry about it. How is the addition happening? Is it signed or unsigned? This one is actually signed because there is another variant of this addition operation instruction, which is add u. Another register type instruction falls under the category of arithmetic instructions. However, it is for unsigned representation. So adding things as if they were unsigned. This one is for signed 2C addition. So the numbers are in 2C, the answer is in 2C. Questions about this example? Good. It will overwrite it. That's a good question. So what if there is something in A? What if there is something in S0? I would have overwritten it. Yep. So it's sort of the up to the user, up to the programmer to kind of be careful about that. Or use a temp register, right? So don't try to use the saved one. Other questions? Okay. Next, let us talk about the two instructions. In fact, the only two instructions that have things to do directly with the memory. With the memory, you may be interested in one of two things: bring things from memory to register file, or store things from the register file to the memory, right? So what I like to do is have my small register file over here and a big memory over here, right? So when you're executing instructions such as the add instruction, you are within register file, right? You're here. Register file is over here. Memory is over here. Load and store, load word and store word to be specific, those fall under the category of I type instruction, immediate type instruction. Again, more details about these things, but just want to say it because I thought about that. I type instruction. Load and store word are the two data transfer instructions. How is load word going to work? Bring a word, bring 32 bits from the memory to a register. How is the store word going to work? Exactly the opposite way. I have the results in a saved register. Store them onto memory, right? Store word. Now, when I say load word, what do I need to think about first? Where am I getting the thing to, right? Which 32-bit register is it going to, right? I have 32 choices. Where am I loading? What do I need to give it? A 5-bit sequence to identify which register is your destination register. Yeah? What else? I also need to talk about this, right? What is the address in the memory? From where do you want to bring it to this particular register? Now, when you're specifying the address in memory, you can do it in a very interesting fashion. You don't need to give it one at you could give it the address, or you could give it an address that is a base address plus an offset. So the offset, you can sort of move away in either direction away from the base address. So if you have a base address, you can sort of move plus or minus, up or down with respect to that base offset, base address, because of another field called offset. It is a 16-bit field. So you have a limited range for that. But you can work off of the base base address. Where should I store the base address? In a 32-bit register. So base address in a 32-bit register. Offset directly part of the instruction itself. Destination register, another 32-bit register in the MIPS register file. Load word. So let's take a look at load word now. Load word, the mnemonic is LW, load word. S1, what is that? Wherever things are going to, destination. What is the offset? A 16-bit number that can get added to the base address. Where is the base address? Provided in S2. That's your base address. Again, offset can be provided as a 2's complement number, 2C number. So it can be plus, it can be minus, it can be signed. So let's take a look at the meaning here. The destination is $S1, so number 17, right? Register number 17 is where things are going to. What are you reading from? You're reading from the memory. What is the address? Take the base address, add the offset to it, access the memory, so do a memory read, and put the result in S1. You see that? How many bits do you need for S1? 5. S2? 5. Offset? 16. Where are the rest? Opcode for load word. Is that? So for ITAP instruction, that is going to be the format. Opcode, source register, destination register, the offset, the immediate field, the 16-bit field. Now, for different instructions, the immediate field, the 16-bit field, can be used differently. So for example, for load word, you are using that as the offset for an address. For add I, suppose you wanted to add a constant to a register, you use a add I instruction, also called as the add immediate. So when you're using that instruction, there, this same 16-bit immediate field is used as the constant, right? So depending on what type of instruction it is, you're using the same 16-bit immediate field for load and store word as an offset, for add I as a constant. Questions about the load word instruction? It's very easy to sort of get confused between the base address and the destination, right? Like so, a quick picture, register file here, memory here will help. Go ahead. The offset is what? Oh no, it is part of the instruction. So wherever you are writing the instruction, maybe in the instruction memory. So when you read that instruction to the instruction register, you have that number right there. Right, from the register file. Absolutely. It is literally the part of the instruction itself. Let's see, store word. How is that working? Oh, go ahead, Ben. Yeah. Yes. So like last 16 bits are literally the offset. Next, what are we saying? Store word. For store word, things are going to go the other way, right? So whatever, so I need to talk about what? Which register you want to store, right? So I can just give it a number. Where is that? Right here. Again, so I'm taking the contents of the 32-bit contents of $S1, one of the saved registers, and storing it where? Take the base address,
Add the offset to it, you have got the target address. Same as before, but now things are moving from here to there, right? So whatever you have in S1 is being stored in memory. Where in memory? Take the base address, add an offset to it, you've got the target address. That's where you want to store the contents of S1. Just the opposite, right? Questions? Oh, go ahead. So we actually have hardware inside our data path to execute that add. So that's like, that's exactly where we are going, because in order to support all these instructions, we are going to need multiplexers, adders, shifters, flags, ALU, a lot of other hardware. So our goal for the next 4 or 5 lectures is going to be to get to that particular block diagram, right? Can I see the whole thing, whole data path? A little bit overwhelming, but it's going to be, the only way we can make things a little bit organized is look at one aspect, then the other aspect, then the other aspect. So follow the life cycle of the instruction. Then we'll be able to get to it. Eventually, you guys will be very, very comfortable with it. That's sort of my goal here. But that's a good question. The question for those of you who are online, the question was, if I wanted to do this offset plus base address addition, do I need to execute another add instruction or not? The answer to that is we don't need a separate add instruction for that. We, in fact, will have hardware inside our data path that will support that, because we need support to be able to carry out instructions. Let's see. Here, this is another very interesting example, because this sort of goes into the byte versus the word conversation. So what are you doing here? We are trying to compile very innocent looking instruction here, just an addition. What do you have? G equals H plus a memory array of the name A, and you're taking the 8th index of that memory array, adding that to H, storing the result in G, right? So what are you going to need to do? You are going to need to do an addition here. But before you do the addition, you are also going to need to do the load, because you need to access that memory array. So how are you doing that? Well, the way we start is this. We are assuming that the variable G, we are using the register S1 for that. And S2 for H. And we also, because this is a memory array A, we are going to need to know what is the base address for that A, which is A of 0, the 0th index. What is that base address? And we are using another register for that, S3. So we have got G, we have got H, and then we have got the base address of that memory array. Yeah? Next. We are going to do this in 2 steps. One, bring this particular word into memory, bring this particular word from memory to the register file, add. 2 steps, right? So the first step is load word. Which word are you loading? You are loading S3 has the base address, right? 32 is the offset. So this should be a little bit troubling now, right? Why is the offset 32? I thought the offset should have been 8. Good. Exactly. We are going to bring words. However, we are going to address things byte-wise. Byte addressable, but word accessible. Addressable versus word aligned data transfers. So 8, that particular offset is in the form of a word, but the offset needs to be provided in terms of bytes. So I need to multiply by 4. So take the 8, multiply by 4, you get your 32 as the offset. So how do you actually write it out as a bit sequence? You are going to need to convert that 32 from decimal to a 16-bit binary sequence. That would be your part of the instruction. You guys see that? So base address, offset, add the offset, but don't forget the 4. How are you going to do that in hardware? So like you asked earlier, do I need an addition instruction to execute? Over here, you might have another question, similar question. Do I need a multiplication instruction? Because I need to do 8 times 4, right? We don't need to do a multiplication instruction. We need some hardware to multiply the offset with 4. What do you think that does it? Multiply something by 4. What does it? What hardware will do that? Bit shift, left by 2, right? So we are going to need a shifter for that. Let's see. Okay, so we did the load word. We got things into our temporary register T0. And now all we need to do is take that T0, add it to our H, right? I think H was here. H was S2, and then store the results in G, right? Load word, add, done. Why did we have to do load word? Because we were trying to access the memory as one of the operands for that addition. Questions here? Let's see. How are we doing on time? 9:40. All right, let me try this. All right, let's make this the last slide. All right. I need to preserve my voice a little bit for the rest of the day. I've missed lecturing in person, projecting my voice. So my vocal cords are telling me, hey, remember this? You used to do this in big auditoriums for a long duration of time. The problem is I would sip hot water, at least warm water, while I teach. I can't even take on my mask now. So it's interesting. Let's see, MIPS, loading words, but addressing bytes. Loading words or storing words. But in terms of addressing things, you're doing that byte-wise, which is the reason why we needed to multiply by 4 earlier. And arithmetic operations, even logical operations, are going to be on registers. Some of the arithmetic operations are going to be R-type, like add, and some of the arithmetic operations are going to be I-type, add immediate. We'll take a look at those immediate instructions next class, next Monday. Now, just to quickly summarize instructions and their meaning. On the left, you have the instruction, add S2 and S3 and put the results in S1. Its meaning. Subtract, well, now things matter. The order matters now. The destination is still S1, but it is doing second minus third operand. So S2 minus S3 goes in S1. Signed subtraction. Next, load word. We talked about that, right? Bring things from memory to a register. Store word, opposite. Take a register and put things into a memory. And while you are accessing the memory, you need a target address. The way you compute the target address is base address in a register, which is part of the register file, and an offset, which is a 16-bit field, which is part of the instruction itself. So that's sort of where I think this is, I really want to keep going, but I will stop. I think it's a little bit too much for the 2 days. Let's see. Oh, sorry. Just want to keep track of, yeah, I think we are okay. All right, let me stop over here. You guys can work on the activity. I will see you guys Monday of next week. 8 a.m. sharp. Let us stop recording here now.